Hey guys, it's Ms. Marflack here. We're moving on to our next lesson in our Introduction to Calculus, and we're continuing with limits, and now we're going to be taking a look at limits algebraically. This is the last representation of limits that we're going to analyze. We're going to be doing some more work with limits after this, but this is going to sum it up for the three representations: graphically, numerically, which is tables, and then algebraically. Algebraically, I do think is probably the most complicated out of all of them, but those of you who maybe have a good grasp on your Algebra 2 skills, like simplifying complex fractions and rationalizing and things like that, then it shouldn't be too bad. But where we spent maybe just one day on graphically, one day on numerically, we are going to spend probably 2 or maybe even 3 days on limits algebraically. Now, the good news is with limits algebraically, there is not a lot of notes. We just have a short definition to kind of get us started, and then we're going to jump in and we're really going to be taking a look at a lot of example problems today. The first type of limit algebraically problem that we're going to be work with is called direct substitution. And direct substitution is probably the easiest way to solve for your limit or evaluate your limit, but you can only do direct substitution in a very specific case, and that's when the function that you're given, which is right next to the limit, is either a polynomial or it's a rational function. So a rational function has that numerator and that denominator, and both the numerator and denominator of the rational function is a polynomial. And then we're going to have our a again, the limit as x approaches a, and our only thing here is that a has to be in the domain of that function of f. And then if this holds true, so if it's a polynomial or it's a rational function and a is in that domain, then here's the rule that we're going to follow for the direct substitution. Our limit as x approaches a of f of x then will be equal to f of a, which means that you just directly plug this number into the function and you get out your number or a function. Okay, so once again, you plug this number into the function, directly substitute it into the function, and you're going to get out a function. We saw in our limits numerically and algebraically that sometimes this is not true, but every time it wasn't true, it's because you had a piecewise function. So here's that condition again where it has to be a polynomial or rational function. So one of the first things you look at is to see, well, is there any way that I can just directly put the x value or the a value in and get out a number? And most of the time, direct substitution will work the first time, and then we're just going to have some other properties that they're probably not even worth naming, but you know, we'll put them here. That way when we see an example problem, we're not that confused. And here's going to be the first one. You can also have your limit as x approaches a of just some constants. Let's say that constant's 5 or 6. Then your answer is going to be equal to that constant. So keep in mind this is a function here. So this will be a horizontal line. So no matter what x value you're at as you're approaching that horizontal line, your y value is going to be that function. So we have the limit as x approaches a of a constant is equal to that constant, or you have the limit as x approaches a of x is your function, and that's going to be equal to a. This one trips a lot of people up, so we'll see this one in action as well. But the main thing is we're not doing too much algebra. We're really just directly substituting in and see if we get out a number. That's in the case of a polynomial and a rational function. And then if we have the limit as x approaches a of a constant, it's equal to that constant, or the limit as x approaches a of the function x is equal to whatever number or x value that we are approaching. All right, we're going to switch colors here because we're going to move on to our example problems, and we're going to get started with a few, and our directions here are going to be evaluate. So I want to see what this limit is equal to. All right, here we are, number 1. We're going to do the limit as x approaches 2, and then here's my function, x squared plus 6x all over x to the 4th plus 3. All right, this is a perfect example of direct substitution. This is what we call a rational function. We have a polynomial in the numerator and a polynomial down in the denominator. Now, the limit notation carries all the way through the problem until you substitute in. Once you substitute it in, then the limit notation is gone. You're done with the limits. You're now evaluating. So there's no simplifying we're going to do here. We're just going to go ahead and do direct substitution because it's a rational function, and we're going to plug in 2. So once I start plugging in and directly substituting, once again, that limit notation is gone. So I'm taking that a and I'm evaluating f of a. I'm putting a right into the function. Here a is 2, so I'm putting 2 right into the function for x. And then we're going to do some simplifying here, and we're going to have 4 plus 12 all over 16 plus 3, and we're going to get 16 over 19. And then 19 is a prime number, so there's no way we're going to simplify that. And then there's the first one, directly substituting, just putting it right in. Okay, number 2. We're going to have the limit as x approaches, we'll do 3. Now this is not a rational function, but instead now this is a polynomial, and our direct substitution works for rational functions and polynomials. All right, now once I substitute in, that limit notation is gone. Okay, so I'm substituting in 3 for x, and the limit notation is gone. And then now we're going to do 3 to the third is 27. 2 times 27 is 54. Minus 30 minus 8. Work left to right. 54 minus 30 is 24. 24 minus 8 is 16. There we are for number 2. And there's our final answer we evaluated. All right, now we're going to take a look at number 3. And we're going to have the limit as x approaches 4 of 5. All right, this is one of our other intuitive properties from up here, okay? Remember, this is a function here, right? So the function is after the limit notation. So if this function is just 5, that's the line y equals 5. It's this horizontal line. So no matter what x value you're at, if x is approaching 4, if it's approaching -3 or 0, no matter what x value you have, you're always going to approach this horizontal line, which is 5. So that's going to be our answer here is 5. Now, if that's really confusing to you, maybe understanding that this is a function, a horizontal line, yes, you can just memorize the rules, but at some point, rules accumulate, and it's a little hard to memorize the rules. So do try to think of this as a horizontal line. This is a function, y equals f, just like these are functions, right? And no matter what x value I have, my y value is always 5. Or, you know, using this rule here, x approaches a, doesn't matter what a is, of a constant c, your answer is that constant. All right, here's c, and my answer is c. This is a great question to just have on a quiz or test, because it looks simple, but some people give me 4. Or some people do some creative things, they give me 20 or 9, or just random things. They don't really understand the concept that a limit is what is your y value as your x gets closer to 4 of this function 5, which is a horizontal line. All right, right over number 4, we're going to have the limit as x approaches -3 of x. And this trips up a lot of people too, and I don't understand it. X is a polynomial, which means that I could just do direct substitution and I plug in, wherever I have x, I plug in -3. My answer here is going to be -3. And there's that rule here as the limit as x approaches a of x is equal to a. And that's the same thing here. Here's my a. All right, so we're going to see more direct substitution, don't you worry, but I just want to introduce one more kind of last thing to keep in mind here, and then we're not done with this. We're gonna keep doing this, but I do want to introduce one more thing before we keep going. And that's going to be our what we do when we have what's called an indeterminate form. So indeterminate means you can't determine the answer or how to evaluate it. And usually sometimes it's in the form like 0 over 0, you can't determine, or a number over 0. It's okay to have 0 in the numerator, but not in the denominator. Or maybe sometimes, we're not going to see this for a while, but infinity over infinity you may see in calculus. But these, whenever you directly substitute in, so when I substituted in here, I got 16 over 19. If I got 0 over 0, that's what we call an indeterminate form. If I got 16 over 0, that's indeterminate form. And whenever you have indeterminate form, your goal is now going to be to simplify first. So that's the only difference, is when you plug it in, directly substitute, and you get indeterminate form, you want to simplify first and then do direct substitution once you've simplified. Now, once you start getting really, really good at these types of problems, you'll be able to just look at it and maybe not even plug it in to know that you're going to have to do some simplifying first before you evaluate. And then now we're going to switch it back to the light pink, and we're going to continue with these evaluatings. We did 1, 2, 3, 4. We're still evaluating here, and I'm going to number this one 5. And I'm evaluating, and I'm going to do the limit as x approaches 6 of x squared minus 36 over x minus 6. So if you kind of took a minute and you tried direct substitution, which is what you always start with, so we're going to learn a lot of rules with limits algebraically, but always begin with direct substitution. If I plug 6 in here and then 6 in here, I'm going to get 0 over 0. That's an indeterminate form. I can't evaluate. So I'm going to simplify this first. Now, while I'm simplifying, I am not plugging in the 6 yet. which means I still have this limit notation, okay? If you don't have this limit notation, I will take off points because you need to know that once you substitute in, the limit is gone, you're now evaluating. But as I'm simplifying this, I still have this limit notation. And you should be feeling pretty good with factoring, okay? We've done a lot of factoring this year. Maybe if you need a refresher, go on Khan Academy, look up some Algebra 2 videos on factoring, but this is our difference of two squares. We take the square root of the first term, square root of the last term, and we do our opposite sign. Oh, I put 4. Opposite sign in the middle. All right, and then now we can do some simplifying. X minus 6 over x minus 6 is 1. And then I'm still simplifying here. I have not actually plugged in x approaches 6 yet. Okay, so I simplified my limit all the way. And then once I've simplified it all the way, now I can do direct substitution. And then when you do direct substitution, boom, our limit is gone. So now I plug in x equals 6, and then we get 6 plus 6 is equal to 12. So once again, that limit goes all the way through until you directly substitute. All right, moving on, and we're going to take a look at number 6. We're going to have the limit as x approaches 4 of 5x squared minus 80 over x minus 4. Okay, start with the first tool in our tool belt, plug in direct substitute, see if you can get an answer, and I can already see I'm going to have 0 definitely in the denominator. That's our indeterminate form, which means I need to do some simplifying, and I can definitely simplify here by factoring. Now, I don't want you to think that simplifying will always be factoring. As we get on to day 2 and 3, simplifying will mean many different things. It will mean maybe rationalizing the denominator or simplifying a complex fraction. So it's not always going to be factoring, but today it will be factoring. All right, so our goal here is to simplify. So I'm going to factor that numerator, and I'm going to take out a GCF, and my GCF with these first 2 terms is going to be 5. All right, and then we're going to have 80 divided by 5, and that is 16. And then I still have x minus 4 in the denominator. And then there's that difference of 2 squares. So we're going to keep it going with the simplifying, which means I'm still bringing along that limit notation. I haven't directly substituted yet. All right, and then I'm going to factor some more, and we get x minus 4, x plus 4 in the numerator over x minus 4. And then now x minus 4 over x minus 4 is equal to 1, and I'm coming down here now. And we still have the limit notation because we have not substituted anything in yet, and I have 5 times x plus 4. Now, if you'd like, you can distribute this and keep simplifying, but at this point, I see now that I can use direct substitution, and I don't have an indeterminate form, which means I can substitute now, and then once we go ahead and we substitute, now we can drop that limit notation. All right, so that may be, I know your assessments are multiple choice, but that could be a multiple choice question. When do you stop using the limit notation, when solving a problem? And the answer would be once you substitute, you get rid of the limit notation. All right, and then here we are, 5 times 8, and that final answer, you evaluate it, it's equal to 40. All right, here we are, number 7. All right, don't think just because you did these 2 factoring ones that you could stop the video or fast forward. They get harder, and harder, okay? So please stick around. All right, now we have the limit as x approaches 1 of x minus 1, and then x squared minus 4x minus 3. All right, so it's okay to have 0 in the numerator, but it's not okay to have 0 in the denominator. If I plug this in here and I try direct substitution, I'm going to see that I'm going to get an issue here with 0 in our denominator. So then we're going to go ahead, oh, this is supposed to be plus 3. That's why I was just mentally doing it in my head, and I was like, no, you don't get 0. But now you do, because you have 1 minus 4 is negative 3 plus 3 is 0. Okay. And then now, so I know I can't use direct substitution, so let's do some simplifying. And the way we're going to simplify in this example is like the last. We're going to go ahead and we're going to do some factoring. So we're looking for 2 numbers that multiply to 3, but add to negative 4, and that's going to be a negative 1 and a negative 3. Those will multiply to positive 3 and add to negative 4. And then now I have x minus 1 over x minus 1. That is equal to 1. Okay, so notice 0 is not in the numerator. That's equal to 1. Over x minus 3. And then now you're in a place where you're able to directly substitute and get an answer coming down over here. So once I substitute that 1 in, now that limit notation goes away, okay? And I'm equal to negative 1/2, or 1 over negative 2. And there we are for number 7. All right, number 8 may look a little complicated. Limit as x approaches 1, square root of 5x minus 1. All right, now even though it looks like a radical, you could write this with the parentheses and write everything to a 1/2 power. So we can write this as our polynomial, so this we can use direct substitution for. No need to simplify here. So I'm just going to plug in 1, and then once I plug in and directly substitute in for 1, the limit notation is gone. It goes away. We're going to have 5 minus 1 is 4, and we're really only going to be working with the principal roots here, and that's going to be 2. So the answer is not -2. Remember, when you apply a radical, you take plus or minus, but when a radical is just in a problem, it's assumed it's a principal root, and you just take the positive answer. All right, there's number 8, and we're going to take a look at number 9. We're going to keep it going here. And we're going to have the limit as x approaches 4 of -2. All right, and there's one of our rules from the very first page, or one of our other properties here. And here's our function -2, which is a horizontal line. So whatever my x value is, my y value will always be equal to -2, and there's my answer for number 9. All right, a few more to go here. Number 10, maybe I should put over here. No, number 10's a little long one. I'll keep it going down here. Number 10, the limit as x approaches -2 of x squared plus 7x plus 10 all over x squared plus 2x. All right, if we took a minute and plugged this in here, we're going to get +4 minus 4, and that's going to give us 0 in the denominator. We're in our indeterminate form, so let's do some simplifying. And simplifying in today's lesson is going to mean factoring. So those two numbers that are going to multiply to 10 but add up to that middle number 7 are going to be 2 and 5. And then this is a GCF factoring, taking out my greatest common factor, which is x, and I'm left with x plus 2. And then x plus 2 over x plus 2 is equal to 1, and we're going to keep it going with simplifying the limit. Nothing's plugged in yet, which means I have x plus 5 over x. Once I go ahead and do that direct substitution for x, then the limit notation is gone, and we're going to get 3 over -2, or -3 over 2. All right, and then there we are for number 10. Moving on to the next page, how many more I got for us? 1, 2, 3. 3 more. Okay, good. 10, this one's going to be 11. And we're going to have the limit as x approaches -4 of x squared plus 8x plus 16 all over x squared minus 16. I got a lot of people last year on a quiz with this question. And I did not think it was that complicated, but I put a big star in my notes to definitely do this example problem with you guys. All right, so stick around for this one and focus here. It looks simple, which means there might be a little trick to it at the end. So let's go ahead. We're going to factor, because when I plug in -4 and I squared in -16, I get an indeterminate form there. So instead, we're going to factor my two numbers that multiply to 16 but add to 8 are 4 and 4. And then my bottom factoring is that difference of two perfect squares. And then x plus 4 over x plus 4 is equal to 1. So I'm able to take out those factors. And then now here we are, and there's nothing else we can do, and it's fully simplified. And then a lot of people were giving me, oh, it's undefined or indeterminate. No, now it's fully simplified. Let's plug in that -4. We have -4 plus 4 over -4 minus 4. -4 plus 4 is 0. -4 minus 4 is -8. And then a lot of people were saying, oh, undefined. No, 0 is okay in the numerator. All right, this is equal to 0. All right, 0 is a-okay in the numerator. All right, and then notice once I plugged it in, I got rid of my limit notation. Okay, 2 more to go. Number 12, and we're going to have the limit as x approaches 6 of 5x cubed minus 30x squared. Ooh, we got a big polynomial here, but we do know how to factor polynomials like this one. All right, and we can see we have 4 terms here with this polynomial, which means we're going to go ahead and we're going to do some factoring by grouping. So I want to group these first 2 terms together, and I want to pull out my GCF, and my GCF is a 5 and an x squared. So I'm going to pull that out, 5x squared, and I'm left with just x minus 6. And then I pull out anything in common here, and whatever's in common is just a positive 3. And I'm left with x and then minus 6 as well. And then you see where this is going, and I got an x minus 6 in the denominator. All right, coming down here, I pull out my GCF, which is x minus 6, and I'm left with 5x squared times 1 plus 3 times 1. And then x minus 6 down the denominator. There's that factoring by grouping. If you're not comfortable with multiple terms like this, go ahead and go on Khan Academy and review your factoring. X minus 6 over x minus 6 is equal to 1, and then we're just going to be left here with 5x squared plus 3. Once I go ahead and I substitute in, the limit notation goes away and it is dropped. And then simplifying some more, we got 5 times 36 plus 3. 36 times 5. We have 0, 3. In this class, we're not using calculators, right? So we got 180 plus 3, and that's going to be 183. And then you may be saying, Miss Martha, you're crazy. I'm home now. I can use a calculator. Okay. I won't say anything, but I didn't use one, okay? So you really shouldn't be using one either. All right, here we are. Here's the last one, number 13. Limit as x approaches -2, and this one's also an interesting one. A little different than the factoring by grouping above. It's going to turn out different. Okay. When I go to plug in x approaches -2, you could take the time to plug it in. You're going to see you're going to get an indeterminate form. I can see that just from the denominator there. We have 4 minus 6 plus 2 is going to be 0. So I want to factor, which means I'm going to factor by grouping up in the numerator because I got a lot of terms. So I'm going to group these first two. I'm going to pull out an x squared, and I'm left with x plus 1. And then I'm going to group these two, and I'm going to pull out a -1, and that's going to change the sign. And I'm going to have 2x plus 1s now. And then I'm going to factor that denominator, and my two numbers that multiply to 2 but add to 3 are positive 2 and positive 1 here. And then I could pull out my x plus 1, and I'm left with x squared minus 1. And that is a difference of 2 squares. You could keep factoring that if you'd like. But if you keep factoring it, you're going to see that it doesn't matter because it's not going to simplify with anything anyway. So x plus 1, x minus 1, all over x plus 2. That's as simplified as we can get. And then when I go ahead and I kind of take a minute to plug it in, okay, substitute in, we're going to have -2 plus 1, and then -2 minus 1 all over -2 plus 2. That's going to be -3 here. And what am I doing? -1 times -3 all over 0. And that's going to be, going off the page, 3 over 0. And then that's going to be undefined. So this limit does not exist. So we did what we could. We tried simplifying it. It started off in indeterminate form. Sometimes when you simplify it in indeterminate form, it does turn out to exist, and you're able to evaluate the limit. And then sometimes when you try to simplify in indeterminate form, you end up with something that's undefined. And if you took this function and maybe you plugged it into Desmos and then you tried to approach it -2 from both sides, you'll see both sides are not equal and the limit does not exist. All right, that's it for today. Like I said, this is day 1 of probably 2 or 3 days. The next time we meet, we're going to be taking a look at simplifying indeterminate forms without factoring, maybe just a little bit more complicated algebra rules. Just to kind of summarize what we did today, we did direct substitution, we evaluated at a constant, we evaluated at the function x, and we also evaluated indeterminate form, mainly using factoring, and we're going to see this again in the future. We did plenty of examples today together, enough for you to get through your homework. We did 17 examples, 13 and the 4 from the first page. So if you do have any questions, please email me and get to work on that homework.